In the linear variational method, we introduced a trial wave function like this that's given as the linear combination of two basis functions, phi1 and phi2, with a1 and a2 as the two coefficients. That's what this equation here is telling us. Now, once we've defined this trial function, we can use those basis functions to calculate these numbers, hij, which is the Hamiltonian sandwiched between two of those basis functions, or the overlap of those two basis functions, or two of those basis functions, Sij. Once we've defined those parameters, we can then develop our expression for the expectation value for the energy and rearrange that a little bit, and we end up with a pair of linearly dependent equations given here, where the a1s and a2s are the coefficients of the expansion, and they are part of the unknowns that we have, but so is this energy. And because the energy is unknown, we don't actually know. We don't have constants for these coefficients. All right, what we can do is we can take this set of equations and now rewrite them, and we're going to rewrite them using matrix notation. So if I rewrite this as a matrix, I would have H11 minus ES11 for that upper left corner, H12 minus ES12 for the upper right. We'll have the same thing for the lower left, and we'll have H22 minus ES22 in the lower right. All right, so this would be the matrix expressing these things. Now, in a matrix equation, this is multiplying a column matrix, which are the two coefficients a1 and a2. So remember, in matrix multiplication, I take this row and multiply these elements by the elements in this column to get a new column. And what this equation is telling us is that those results equal to 0. So this is how we would write this same equation. This same equation in matrix notation would be written like this, all right, which is a nice sort of slick way of writing down these kinds of equations. It sort of minimizes the extra stuff we have to write. All right, but once we've written this way, the way we would typically solve an equation like this for this pair of coefficients is we would find the inverse of this matrix and multiply on the left-hand side by that inverse. So if this matrix could be written as A, then the inverse of A would be multiplied over here, and we would multiply it also by 0, 0, which would give us 0, 0 on the right-hand side and A1, A2 on the left-hand side. So if the inverse exists, then we would come up with a solution that looks like this. All right, but that, of course, is the trivial solution that we mentioned in the previous video. So we don't want that to be the case, and it turns out in matrix algebra, the condition that prevents a matrix from having an inverse is if its determinant, and so I'll write that determinant now with solid line brackets, so its determinant would be given by the same expression, at least the same elements inside. But now that we have a determinant, this is actually a number, and we say that it's equal to 0. So this is that equation, that secular determinant equation that is needed in order to find the solution for this 2x2 problem. Okay, 2x2 is fairly easy. I mean, we could immediately write down this determinant. Remember that the determinant of a matrix, say A, B, C, D, is just A times D minus B times C. That's all it is. So it would be this element times this element minus the product of these two elements would be equal to 0. All right, a 2x2 is not a terribly difficult problem to navigate. What happens if we have a much larger problem? What if we have many states that are used in this expansion for the trial eigenfunction? Well, the generalization of this secular determinant equation might look something like this. Again, we would have H11 minus ES11 in the upper right-hand corner, and in the next diagonal, whoops, let me clean this up. In the next diagonal, we would have H22 minus ES22. The off-diagonal elements would be as we've written. So all I've done is reproduce that 2 by 2 determinant up here, but the next one over here would be H33 minus ES33, and this would keep going on down till we have HNN minus E times SNN. And then there's another straight bracket over here terminating the determinant. Okay, and these would continue on in this fashion. We'd have H1n minus ES1n on the far right-hand side of the determinant, and same in the far bottom right corner. Okay, so all of these elements would be filled in with their appropriate expressions. And this is the thing that would be equal to 0. So this is the secular determinant for an n by n problem, or an n, it basically would be for n basis functions included in our trial function expansion. So solving this equation now is the one that we would need to solve in order to get the variational answer. Well, the good news, it looks like this is a pretty hairy thing, and in fact finding the determinant for this would be an involved operation for anything greater than a 3 by 3. But it turns out that for large n, there are handy routines that can be readily solved on a computer. So we'll just say solved on a computer. You don't have to do this by hand. And so that's what makes these problems more achievable for large basis sets and large expansions. Now I want to take this a step further and consider that what if we had chosen a basis set, and so by a basis set I mean the set of functions phi sub I. What if we had chosen a set of functions that were in fact eigenfunctions of a Hermitian operator? What do we know about those functions? Well, we know that phi I, phi j is going to equal 0 if I doesn't equal j. If we make them normalized, then it equals 1 if I equals j. Well, that makes this secular determinant look a lot simpler. Now, instead of having all those elements, what we'll have is the following. We'll have h11 minus e, and since s11 is equal to 1, I don't have to write the s. I'll have h22 minus e, and so forth, down to hnn minus e. For the off-diagonal elements, I'm just going to have h12 and h12 down to h1n and over to h1n. So you can see this is a much more concise secular determinant to solve, and so it represents an easier problem to solve, even algebraically by hand, but also by computer. So I will call this the standard matrix eigenvalue problem. So basically the idea is that by solving this determinantal equation for the energy, we will get energy levels for the system. Now, what are these energy levels? How many of them are there likely to be? Well, it turns out that one can show that if this is an n by n determinant, that there will be exactly n solutions for the energy. So in other words, n different energy levels that we would get from this particular solution. Once we have those n solutions, we can then plug them back in to the secular equations. So for example, E1, all right, I would plug that into my initial equations, and I could use that then to solve for the coefficients that go along with that. So for example, that might give me a set of coefficients, A1 for eigenvalue 1, A2 for eigenvalue 1, all the way up to AN for eigenvalue 1. For the second energy, I would again have a set of solutions A1 for the second eigenvalue, A2 for the second eigenvalue, down to AN for the second eigenvalue. And I could do this for each of the n energy eigenvalues. So each of these represents a different eigenfunction for this eigenvalue. So again, we see the correspondence between eigenfunctions and eigenvalues, but now they're coming out of a matrix operation. And it turns out these matrix operations are tailor-made for large-scale computing. And so this is one reason why these techniques are by far the most widely used for determining the quantum states of a variety of different systems. And they're the ones that would be used, for example, by the program Gaussian or Spartan or one of those other things to find the solutions for these different types of quantum systems.